So in general, what we're going to be trying to find is we're going to be finding the relation between the adiabatic saturation temperature and that wet bulb temperature. So in part 2, we found that wet bulb temperature equation. We're going to work with that to find an equation in for the adiabatic saturation temperature. So to start us off with that, we're actually going to be using energy balances here. So we have an enthalpy of this going in and an enthalpy going out, but because it's a closed system, those enthalpies are going to be the same. And so working with that, we're going to write the equations out for both of those. The equation for enthalpy in is that airflow of it going in times the heat capacity, which is multiplied by the temperature going in. And that is added to that heat of vaporization of the water, which is then multiplied by that pressure of the water times the molecular weight there, all over that universal gas constant and the general temperature there. But we're also going to want to take that, we're actually going to want to flip it over and get an inverse of it. But on the inverse side, we're going to have the total pressure and the average molecular weight. We're going to have P total and average. Okay, and so that is for the enthalpy in. For the enthalpy out, don't have as much room, but I'm going to still try to get it in. We have the same thing. It's generally the same thing, but the difference is that temperature is going to be the temperature going out. That heat of vaporization is the same, but also here, instead of that partial pressure of the water, we're looking at that saturated pressure of the water. So we're getting that saturated pressure of the water, temperature T, times that molecular weight over RT. And again, we're doing the inverse. It's going to be the same thing here, where we have that RT, that universal gas constant times the temperature, over the total pressure times the average molecular weight. So with that, we have a lot to kind of dissect here, but it's not as bad as it seems. It's a lot to write, but we can work with it. The first step, obviously, we can get rid of that airflow there because it cancels out, it's equal, it's a closed system. That's how it works. The other part that we're going to do is we're actually going to take this section here and this section here. We're going to take this part and we're going to subtract it over here because we're going to get those similar groups. And then we're going to take this and subtract it over to this side to get these similar groups. The reason why is we can then actually take a lot out, and so we can get that subtraction to essentially not be all these big groups you're going to see in a second. Before we do that too, I'm going to say these will also cancel out because it's multiply one over the other. So essentially what we're doing is for this right here, that heat of vaporization, pressure of the water times the molecular weight over that total pressure times the average molecular weight. Here it's the same thing, but the saturated pressure of the water. We're essentially going to take all these similar values and we're going to pull it out. And we're going to have it that it's going to be distributed back in. So you'll see right here as I read it out, we know that this heat of vaporization is on both sides. We know that that molecular weight is there. We know that the total pressure is there, but it's at the bottom here. And we know that that average molecular weight is there. And what leaves us with that is that pressure of the water, the partial pressure of the water, and the saturated pressure of the water at that temperature, but they're subtracted from each other. And the same thing goes on the right side here, where we have that heat capacity and the temperature in and out, except it's a lot easier because we only have to worry about the heat capacity there. So we have that heat capacity, and then it's going to be the subtraction of the temperature out by the temperature in. So that is the equation that we're getting for the adiabatic Saturation temperature. It's a tongue twister for me, I apologize. But now we're going to go back to part 2 and we're going to show the relation between these two. It's actually going to be really cool once you go through it. So from here, we knew that we changed this around to get it that it's going to be the pressures, the partial pressures here, and we changed that density there, that rho there, to be the total pressure there. So we're rewriting this, but we're rewriting with the pressures. We already did this in part 2, but I'm just going to show it once more. Pressure of the water over RT, and we're going to generalize the T's again, because again we proved in part 1, or part 2, I apologize, they're about the same. And it won't even matter in the end of it. The pressure of the water, the saturated pressure there, at that temperature T, minus the pressure of the water, or RT. And that is going to then be equal to, and we know that that rho changed into the total pressure over that RT. And we also still have that average molecular weight, that heat capacity, and these temperatures go by the temperature of in minus the temperature of out in this situation, exactly. Here we can get rid of these RTs. We know they cancel out. We already proved that in part 2. And actually, if you already can see it, that's great. If not, I'll still explain it. These are essentially the same exact formula. What we're doing here is this total pressure and that average molecular weight is just moved to the denominator here. We divide it from this side and move it here. The other difference is that both of these are flipped. So here we have it as the partial pressure of the water subtracted by that saturated pressure of the water at that temperature, and we have T out minus T in, the temperature out minus temperature in. But this is the exact opposite. That's not bad, because since they're both the opposite, we can go ahead and just flip it, because really what it is we're just multiplying by -1 on both sides. That just takes those values, flips them over. So we're going to move this down here. We're going to divide by that P total and the average molecular weight. And also multiply that by that -1, and that gives us the final answer. And it is that we can flip those over. And so as you can see, these are the same. I will be adding that little. This is for the water, the heat of vaporization of water. And past that, you can see that they are the same. So we know that from this is the wet bulb temperature equation, and this is the adiabatic saturation temperature equation. So we can see from this, we've proven that both of them are the same.